Today we are continuing with the second example. So this is the example. Baking soda, which is sodium hydrogen carbonate, is often used as an antacid, meaning it works to neutralize the acid, right? It neutralizes excess hydrochloric acid secreted by the stomach, and that's the reaction there. So you've got sodium hydrogen carbonate, which is solid, and hydrochloric acid, aqueous, of course. Okay, let me just allow this person. Yeah, and then there you've got sodium chloride, and then you've got water, which is liquid, and then carbon dioxide in aqueous. So milk of magnesia, which is an aqueous suspension of magnesium hydroxide, is also used as an antacid. And there you've got the reaction. Which is the more effective antacid per gram? Sodium hydrogen carbonate or magnesium hydroxide. So and then they're asking us per gram. So the fact that we are comparing these particular antacids per gram, meaning in our calculations, we are going to be working with a gram, okay? Then basically what we're trying to do in this question is looking at each equation and finding the number of moles for sodium hydroxide that exist in 1 mole, and then relating to the number of moles with which this particular sodium hydroxide reacts with the number of moles of what? Of the hydrochloric acid. So it means that the one which reacts with more hydrochloric acid, it means that that's the one that is what? That is more effective. Because remember, what's the function? What's the use of the antacid? It's so that it can be able to what? To act against the acid. So here we are going to use gram for each, and the reason is we are comparing per gram. And then we're going to find the number of moles for the sodium hydroxide and the magnesium, for the magnesium hydroxide and sodium hydrogen carbonate. Then from there, relate using the what? The mole ratios, just like we did last time. Then we're going to relate using the mole ratios, and after we do that, then we're going now to relate with the hydrochloric acid, and then from there we can figure out, say, oh, okay, so 1 gram of this antacid reacts with this much moles of what? Of hydrochloric acid. Then from there, the one which will react with, or which will neutralize more hydrochloric acid, means that that's the one that's what? That's more effective. Does that make sense? Okay, so that's what we are going to do. So what we are having is, so this is the example. This is the example 3.16, right? Okay. So the equation that we have for sodium hydrogen carbonate is this, plus hydrochloric acid. So remember, what did we say first has to you have to do for these things? You first want to, of course, check that the equation is balanced before you start your calculations, right? Okay, so then here you've got sodium chloride aqueous, then you've got water, which is liquid. So just because of lack of space, I'm just going to write it down, the carbon dioxide down. So carbon dioxide is dissolved in the water. Okay. Okay. So then, so we've got that. So here what we're going to do is, we know that the what? We know that the masses we're working with is what? 1 gram. So let's first go for the sodium hydrogen carbonate. So we know that we find the moles by saying mass in grams over molar mass. Oh, yeah, molar mass. If you're talking about an atom, sorry, if you're talking about a molecule, and then if you're just talking about an atom, we call it atomic mass, isn't it? And this is in grams per mole. This is in grams per mole. Okay, so what mass are we using? We've already agreed that we'll be using 1 gram because of the reason that I explained. So you've got 1 gram here over the molar mass. We know how to calculate the molar mass, so I'll just write it since we went through that topic. But again, remember, like I said, the chemistry department very particular, so you have to show it. how you're finding this smaller mass, you'd have to show it. But since we already did it, so to save on time, we'll just proceed. So this gives us more. Okay, so it gives us that moles of sodium hydrogen carbonate. So meaning 1 gram of sodium hydrogen carbonate actually has this number of moles. Then again, that's after you've checked that the equation is balanced, right? In which yeah, already checked it's balanced. Now you want to now check the what, the mole ratios between what, between this same sodium hydrogen carbonate and hydrochloric acid. What's the ratio? It's 1 to 1. So since the ratio is 1 to 1, so then let's now figure out, figure out, so since the ratio is 1 to 1, so let's now figure out the moles of hydrochloric acid. Again, since the ratio is 1 to 1, so we even know that the ratio is going to be what? The moles are going to be the same, isn't it? But we just need to show our working. So showing the working, you're going to say, since the mole ratio, is 1 mole is sorry, it's supposed to be 1 mole of hydrochloric acid. Okay, so it's supposed to be 1 mole of hydrochloric acid is equal to 1 mole, okay, is equal to 1 mole of yeah, 1 mole of hydrochloric acid is equal to 1 mole of sodium hydrogen carbonate. So relating the number of moles, we'll say the number of moles that we found for sodium hydrogen carbonate were these. Okay, so this was for sodium hydrogen carbonate. So to convert this, we want to have the moles for the hydrochloric acid. So the hydrochloric acid is the one that's going to be on top. Okay, so that the sodium hydrogen carbonate can cancel down. So remember, show your working, even for finding that molar mass. I just skipped it because we already did it, so to save on time. So you cancel that and then you're going to get the what? The moles. Please show these steps. The chemistry department is very particular. Okay, so here we have it. So we know that 1 gram of sodium hydrogen carbonate is going to react with this amount of hydrochloric acid. So now let's now check, what about magnesium hydroxide? So we've just answered part of the question. So now let's now ask ourselves about sodium hydrogen carbonate. Sorry, about magnesium chloride. So let's see if we can create some space this side. Yeah. So then for magnesium, let's just use another ink. So for magnesium hydroxide, okay, so again here we want to write its equation and be able to check it whether it's first balanced before we start calculations. So this is going to be this. And then you have, okay, so someone to tell me whether this is balanced or not. So someone to tell me, is this balanced or not? Is it balanced? So again, so here what we've discussed. So here concerning with what we discussed, To balance this, we're just going to add the 2 front of this and in front of that, so this becomes balanced, right? So since it's balanced, then what we're going to do then is we're going to find the moles of magnesium hydroxide that are in 1 gram. So 1 gram, the molar mass is 52, oh sorry, rather 58.32 gram per mole. So number of moles is 1.71 times 10 minus, okay, there, moles of magnesium hydroxide. So here again, we then want to now check using the what? Using the mole ratios. So using the mole ratios again, we want to look at the ratios. What's the mole ratio between, so here there is 1, here there is 2, so what's the mole ratio? So the mole ratio is what? 1 magnesium hydroxide, 1 mole of this is equals to what? 2 moles of hydrochloric acid. Okay, so now with this ratio, we can then be able to proceed and then be able to relate now to say, okay, so if we had that 1.71 times 10 to power negative 2 moles, then how many moles of what? How many moles of hydrochloric acid did we have? Again, we know that we just multiply that by 2, but we always want to show our working. So what we're going to do is going to say, so I'm going to have that moles of magnesium hydroxide, and then we're going to have, since we want to convert to hydrochloric acid, so hydrochloric acid is going to be the numerator, then here 1 mole of magnesium hydroxide, so that this can cancel. So then what we're going to have, this cancel and this cancel, so we're just going to have 1 that multiplied by 2, so it's going to be 3.42 10 to power minus 2 of hydrochloric acid. So now the question remains is, when you look at, okay, so what this basically means is that when you look at these particular compounds, right? Okay, let me bring them like this. So you see that 1 mole, or rather 1 gram, let's go with 1 gram. 1 gram of sodium hydrogen carbonate is going to neutralize what? 1.19 times 10 to power negative 2 moles of hydrochloric acid. Whereas for magnesium hydroxide, you see that what's going to happen? You see that 1 gram of magnesium hydroxide is going to neutralize what? 3.42 times 10 to power 2 moles of hydrochloric acid. So you see that, of course, so therefore you just write, since 1 gram of sodium hydrogen carbonate neutralizes 1.19 times 10 to power negative 2 moles of hydrochloric acid, and 1 gram of magnesium hydroxide neutralizes 3.42 times 10 to power negative 2 moles of hydrogen chloride or hydrochloric acid. Therefore, magnesium hydroxide is the more effective antacid, right? So that's how you want to answer that. So that's how you want to answer that. So now let's now talk about the concept of the limiting reagent. So let's talk about the concept of the limiting reagent. So, okay, so let's talk about the concept of the limiting reagent. So here, what I want to understand is, look at this. If you've got 2 slices of bread, 3 slices of meat, okay, 3 slices of meat, 1 slice cheese to make a sandwich, right? Now, that equation, those are the things that you need to be able to make the what? To be able to make the sandwich, right? Now, assume that now you go for work and then you find 8 slices of bread, 9 slices of meat, 5 slices of cheese. Now, how many sandwiches are you going to make? Now, here you've got some things which will be in excess, and so here, what is going to determine the number of sandwiches that you make is going to be the thing that's going to run out first. Okay, so here we're going to look at the thing which is going to run out first. So if you look at that equation that we have there, and you look at the bread means what? One sandwich makes or requires what? 2 slices of bread. So you see that with those 8 slices of bread, you can make 4 sandwiches. Then with meat, you can make 3 sandwiches. Then with cheese, you can make 5. So that means that even though you can make 5 sandwiches using that particular, okay, using that particular cheese, okay, using that particular cheese that you have, you then realize that with bread you can only make what? 4 sandwiches, isn't it? However, interestingly enough, with bread we can make but however with the meat is only allowing you to what? To make 3 sandwiches. Now the question is, how many sandwiches are you going to make? Okay, so again, from there we see that the number of sandwiches that you are going to make, you're only going to make 3. Why? Because that those are the amounts that you make. If you try to make 4, the meat would have run out. If you try to make 5, then both the bread and the sun and the meat would have run out. So basically, what this basically is telling us that in our calculations and in these stoichiometric calculations, it's important to find the limiting reagent because it's going to help us figure out what amount of product is going to be formed. Because here's the thing: when you are when you are doing a reaction, right? When you are having a reaction, when a reaction is being done, what's going to happen is this, okay? So when a reaction is being done, what's going to happen is things are going to be reacting, and so some reactants, some of the reactant may be used up quicker than the others, isn't it? So they are going to be used up quicker than the others. So you need to know so that you can figure out what amount of product is going to be formed. Okay, so this is just what everything here is trying to explain. So the reactant that runs out first and thus limits the amount of products that can form is what? Is the limiting reactant. So for instance, where we had the bread, the cheese, and the meat. So the meat there was the what? Was the limiting ingredient because after we make 3 sandwiches, the meat is done. We can't make 4. We can't make 5, even though the bread can allow us to make 4 and the cheese can allow us to make 5. So that's the concept there. So that's the concept there. So now let's figure out how you can determine limiting reactant. So first things first, there of course, like I said, there are 2 ways to determine the limiting reactant. So one way is where what you're going to do is usually for these questions of limiting reactant and things like that, they usually give you the masses of the reactants. So now what you're supposed to do is you have to find the moles for, from the masses, right, that you've been given for those 2 reactants. And then for one reactant, let's say for this one, for where we've been given nitrogen, right? We've been given 25 kg of nitrogen. So you have to find the number of moles for what? That are going to be in 25 kgs of nitrogen. And then also find the number of moles of hydrogen which are going to be present in 5 kg. Then you are then supposed to use their mole ratios to figure out, okay, with this nitrogen that I have, since the mole ratio is 1 to 3, isn't it? 1 mole of nitrogen reacts with 3 moles of hydrogen. So this means that the number of moles that you would have gotten for nitrogen, you multiply them by 3, okay, which is the mole ratio in this case. And so if you realize that the number of moles that you are getting for hydrogen are less than what you have, then that means that the hydrogen is what? is going to be in excess, isn't it? So then the nitrogen will be the limiting reactant. But if you find that the number of moles that you find for the hydrogen is greater, okay, is greater than the number of moles that you have, that means that the hydrogen is going to run out first before the nitrogen. Therefore, then the hydrogen would be the limiting reactant. So basically that's how we are going to do it. So let's do this calculation together, and then we are going to appreciate this concept, right? So let's just go down that route. So we've been told 25 kg, but remember, us in chemistry we don't work with kgs, right? So you are, because now moles, remember, the mass has to be in grams, so I have to convert that mass to what, to grams, and then find the number of moles. So let's go with the nitrogen. So let's go with the nitrogen. So nitrogen, okay, it's just yeah. So the nitrogen, now for the nitrogen, what do we know? So for the nitrogen, we are aware that we've been given, so we want to find the moles, and we've been given mass of 25 kg. Now we don't use what? We don't use kgs, right? So what we are going to do first is convert. Again, like I said, always show your what? Always show your conversions. So what you're going to do is okay, 25 kg. Remember what you want to be, the units you want, they should be the numerator. Then the ones which are cancelling, they should be the denominator so that they cancel. So meaning you're dealing with 25. Again, always show your working. You're dealing with 25,000 grams. So here you write 25,000 grams. Again, over molar mass, isn't it? So what's the molar mass of nitrogen? Remember, here the nitrogen is N2, isn't it? So meaning it's a diatomic molecule. So meaning instead of writing 14, that would write for normal nitrogen when it's alone. This one we're going to say 14 by what? 14 by 2, or to much more easier to remember is 14 plus 14, since there are two atoms, isn't it, of nitrogen. So it's going to be 28. Okay, 28 grams per mole. The same thing we do when we are calculating things such as oxygen when it's like that, and hydrogen when it's like that, right? We multiply the atomic mass so that we get the molar mass, since it's now a molecule and not an atom. So the number of moles that we are going to get is going to be 893. So it's going to be, but we just write it in standard, in scientific notation. But this is 893 moles of what? Moles of nitrogen. That's a lot, huh? And then let's now talk about the hydrogen. Let's use red. So for the hydrogen, we are going to have the mole. The mass is what? 5 kg. So again, like I said, show the conversion over molar mass. Molar mass again, show your working how you're finding it. So you're just basically adding that 1.008, just adding them together, since the hydrogen here is in this form, it's a molecule. Okay, so remember, show your working how you're finding the molar mass, how you're converting from kilograms to grams, just like I showed earlier on. So here the number of moles is going to be 248 moles. Again, I've written this in scientific notation. So moles of hydrogen. So 248 moles. Here it was 893. Now, since we have these numbers, so then we can now do what I said earlier on. So here what you want to do is we're first going to start with what? The mole ratio. What's the mole ratio? So the mole ratio here, the mole ratio, we know that it's 1 mole of nitrogen to what? 3 moles of hydrogen, isn't it? So what we're going to do is we're going to get the moles of nitrogen, and then figure out how many moles of hydrogen are required in order for the what? In order for the reaction to take place. Okay, in theory, isn't it? So we're going to get the moles for nitrogen, which is 893. I'm just writing it in standard in scientific notation. So like this. Then remember, the one that you want to be the one whose moles you are finding should be the numerator. So the denominator should cancel out. So you see there nitrogen is our denominator. So again here you see that cancels and that cancels. So what are we going to do? So here I'm just multiplying those moles by 3. So that's going to be 263. Anyway, not that. Anyway, more than that. 2,680. So there you have it. Moles of what? Hydrogen. So what this is telling you is that for the number of moles that we have for hydrogen, for nitrogen, for the 893 moles of nitrogen that we have, the amount of hydrogen that will react equally with that amount of moles of nitrogen has to be what? 2680. Now look at the number of moles that we have for hydrogen. They are a lot. Sorry, there are fewer. It's just 248 moles. So you see that what's happening. So it means that these amount of moles, the moles of hydrogen that we have, are going to run out whilst the moles of nitrogen are still there. Okay, so basically that's how we can find it. Now let's now use the other way around, where we use the moles of what? We use the moles of hydrogen to figure out this. So again, we're going to use the same ratio, but this time around what we're going to do is we want to use the moles of what? The moles of hydrogen. So the moles of hydrogen are what? 248 moles of hydrogen. So let's now figure out the number of moles of what? The number of moles of nitrogen. Okay, figure out the number of moles of nitrogen which have to react with what? With this. So remember, the one which you want is the one that has to be on top. So nitrogen is on top. Then here it's going to be 3 moles, isn't it, of hydrogen, using the mole ratio. So here we're dividing by 3. Oh, sorry, not 2. It should be in scientific form, to be 248. 248, yeah, it should be in scientific form. So here what we're basically going to do is you're saying, let me get 248 and divide by what? 3. Okay, so this is what? 82.7 moles of nitrogen. So you see, these are the moles that are required for nitrogen. But look at the number of moles that we had for nitrogen, 893. So you see that the nitrogen is in excess, because the amount that was just required to react with the amount of moles of hydrogen that we have is just 82.7 moles. But here we've got what? 893 moles. So it's well over in what? In excess. So that's how you figure out the what? The limiting reactant. Of course, using the first method. Now, so like I said, why is this important? Now, this is very, very important because when you are doing the calculations and you are told, now in this reaction, remember, the product is going to be ammonia. So now imagine if the question was to say, give us the amount of ammonia that would be produced. Now the question is, which moles are you going to use? Are you going to use the moles for the nitrogen or for the hydrogen? Are you going to use the mole ratio of the hydrogen relating it to the ammonia, or for the nitrogen relating it to the ammonia? Here you use the moles of the what? Of the limiting reactant. The reason being is if you use the moles for the one that is in excess, it won't make sense, right? But if you use the moles of the moles of the limiting reactant, it makes sense because you are saying, okay, as soon as these moles are done, the reaction will stop, right? Like the example that we started with for the sandwich, we say, okay, once the meat is done, even if the bread is still there, even if the cheese is still there, we won't be able to make the sandwich, right? So exactly, that's just how we have to think about it. So in this particular example, since we found the number of moles, okay, so we found the number of moles for yeah, so we're able to find the number of moles for the hydrogen. So that means that we have to use the what? The number of moles for the hydrogen, right? Since they are there, since hydrogen is a limiting reactant. So we'll just rewrite the equation so we can be able to follow through. So this is the equation. And then we've got that and that. Then you have 2 nitrogen and that. Okay, yeah, that does it. So we know that we're going to use the moles for hydrogen, and we know that the moles of hydrogen were what? Okay. Oh, okay. Yeah, we're okay. So we're 2000 and that and that. Okay, great. So we're 2.48. Okay, moles. Oh yeah. Oh, so I think yeah, I must have made a mistake. It's actually 2480. Yeah, 200, 400, and yeah. So I actually made a mistake on the number of moles of the hydrogen, but of course, the concept still remains the same. But these were actually the number of moles. I wrote a two instead of a three, so just take note of that, right? But the concept still remains the same in figuring out that the limiting reactant is what is going to be hydrogen, right? But I just made a mistake there. So now, since we've already figured out that the hydrogen is a limiting reactant, so we're now going to use the mole ratio. So the mole ratio for hydrogen and ammonia. So we're going to say 3 moles of hydrogen is equals to 2 moles of ammonia. So then, using the number of moles for hydrogen, which is 2.48 times 10 to power 3. Take note 3, huh? I was making a mistake there. Okay, so take note 3 of hydrogen. Again, what's the way? If you want the moles for something, that thing should be the what? Should be the numerator. So here we want for ammonia, so ammonia will be the numerator. And then over that, isn't it? 3 moles of the hydrogen, the one which we are cancelling. So once you reach at this point, of course, these ones cancel, and then you just multiply again. It's 2 over 3 and that. So you're going to get 1.65 3 moles of ammonia. Okay, now again we know how do we find mass. Mass using moles, we say what? Mass is equals to moles times molar mass. Again, we know the moles. Moles. Pardon me there. We know the molar mass has to be, of course, grams per mole, isn't it? Okay, so here we're going to have the moles. We have them, as we found above. Okay, and then times the molar mass again. We know how to find that. For ammonia, it's 17 grams per mole of ammonia. So the moles cancel. So we're just multiplying that by that. So we're going to have 2.8 times 10 to power 4 grams of what? Of ammonia. So now how would you want to write it? So you would also want to write it as, so converting that to kgs, since we're given things in kgs, so it wouldn't be harm to convert it to 28 kg. Again, you want to show your conversion. So remembering that 1000 grams is equals to 1 kg, so you can show your working there. You have to show how that's being converted. So on the sideline, you'd want, before you write 25 kg here, you'd have to show it. So the chemistry department, like I said, is very particular. So it's very particular, right? So you got that. So what you want to be the unit has to be the numerator on your what's this, on your conventional thing. So here cancels, those cancels. So yeah, they always want to see how you're arriving at things. So that's when you can write it like that. So basically, so you see how you use the limiting reactant to be able to figure out the amount of product. So just take note of that error that I was making with the moles of hydrogen earlier on, but the concept still remains the same. So that's one way in which we can know, or rather figure out, the limiting reactant. And then there's also the other one, but this other one is not usually really recommended. The other method that I'll be showing you, though it's in your recommended book, but it's rarely used anyway. The other one, it's much better, but let's just learn it since it's in the recommended book. So a second method for determining which reactant is limiting. So what you do for this one is you want to get the number of moles like we did. So since we already solved the number of moles, so I'll just explain this one, right? So basically what you do is you get the number of moles for the reactants, right? So in this case we had nitrogen and hydrogen. So what you're going to do is you get the number of moles using the masses that you are given, right? And then you don't then what you do is you then get the mole ratio of the nitrogen with the ammonia, with the product, okay, with the product. So in this case, with the nitrogen with the ammonia, and then separately hydrogen with the ammonia, then you see that the mole ratio of nitrogen and ammonia is 1 to 2, which is 1 mole of nitrogen produces 2 moles of ammonia, whereas the mole ratio for hydrogen is 3 moles of hydrogen produces 2 moles of ammonia. Then what you do is you see those moles of the moles of nitrogen there on top, right? They've been multiplied by the mole ratios to then figure out, say, okay, since the mole ratio is 1 mole of nitrogen gives 2 moles of ammonia, meaning that the number of moles for the nitrogen, to figure out the number of moles of ammonia, you have to multiply the number of moles of nitrogen by 2. So that's what the mole ratio there has done. So you are multiplying that by 2, and you see there we are getting 1790. Yeah, I think it should be somewhere around there, if I'm not mistaken. Or let's just take it the way it is, which is 1.79 times 10 to power 3. So which is 1700 and 1, 2, 3, okay. Yeah, which is 1790, right? So those are the moles of ammonia. So take note of that. Then now again, we get the number of moles for the hydrogen. You see those are the number of moles that we had calculated earlier on from what we had discussed. So you see again, you get the mole ratio, like I said, then you cross multiply. And after you cross multiply, you realize that the number of moles that you're getting for the ammonia, you see, is 1.65 times 10 to power 3 moles. So you see that from what we've calculated, you see that using the hydrogen, we are getting less amounts as compared to using the ammonia. That means because there is a smaller amount of ammonia, which is the product being produced from the hydrogen, okay, as compared to the to the nitrogen, therefore the amount of hydrogen must be the limiting reagent. Therefore, even the moles or the mole ratio that we are going to use to find the mass of our product, we won't use the moles of the nitrogen because it's in excess, like we figured out, right? So we're going to use the moles of the hydrogen, which are those, and then using the mole ratio again, yeah, again, like we used there, we've gotten those moles. So to find out the mass of ammonia, we've got the moles. What do we do? Simply multiply that by the molar mass, which is 17 grams per mole, and there you see we're actually getting the same answer, 28 kilograms. So you can use both ways, but like I said, usually the one used is the first method, right? And there's a reason why it was put first. So but it is just something that you can be comfortable with. You never know these things. Eh? So let's now look at this particular um, example so that we can explore this, and then we can talk about percentage yield. Then we can talk about percentage yield. So the example that we have is nitrogen gas can be prepared by passing gaseous ammonia over solid copper 2 oxide at high temperatures. The other products of the reaction are solid copper and water vapor. If a sample containing 18.1 grams of ammonia is reacted with 90.4 grams of copper 2 oxide, which is the limiting reactant, how many grams of nitrogen will be produced? So first things first, what do you want to do? You first want to what? You first want to write the equation down. Okay, so I first want to write the equation down and figure out, is this equation balanced? And then as the question was telling us, it was even telling us the states in which these particular substances are. So there's no way you can be forgiven for forgetting to put the state symbols. So put the state symbols, and then before you start solving, again, this is a mistake that most people make. Before you start solving, check the equation. Is your equation balanced? So you look at this equation, that's not balanced, right? But since we already went through the topic for balancing, I'll just write the balancing now. I'll just balance this equation quickly. Again, for balancing, we did this, so you can just go through the video. So we are balanced, isn't it? So here now, that's our balanced equation. So now we are given the amounts for ammonia, and then we're also given the amounts for copper. So from here, then we are going to figure out which one is the what? Which one is the limiting reactant? So what we're going to do again, same procedure. So we're going to say the moles for ammonia. They gave us the mass of ammonia to be what? 18.1 grams. Huh? And then the molar mass, again, we did this, so it's going to be what? 17.03 grams per mole. Again, other books will say 17 flat, again, depends. So the moles here is going to be what? 1.06 moles of ammonia. So we now go for the moles of copper 2 oxide. Again, the mass is 90.4 gram over the molar mass of 79.55. So you see, that's why you can't just tell from the masses and say, oh, this one will be the limiting reactant. Huh? Okay, so those cancels, and then we're going to have 1.14 moles of copper 2 oxide. Then what are we going to do again? We have to first figure out the mole ratios, right? So we have to figure out the mole ratios of these two reactants to figure out which one is the limiting reactant, and then that's the one that we are going to use to figure out what amount of nitrogen was actually produced. So the mole ratios between these two is what? It's 2 moles of ammonia is equal to 3 moles of copper 2 oxide, right? So let's go with the moles of ammonia. 1.06. So we've got 1.06. Yeah, so we've got 1.06 moles of ammonia, and then multiplying again the moles for what, for the thing you want, have to be the what, have to be the numerator. So this is the numerator over 2 moles for the, for this, which is the mole ratio. So these cancel and then you get your value. So let's write our value here. Yeah, let's write our value here. So let's just create more space. Yeah. Okay. So now with this, we're then going to have our moles of copper being 1.59 moles of copper 2 oxide. So meaning 1.06 moles of ammonia that we have, it needed, 1.59 moles of copper 2 oxide. But what amount did we have? We actually had 1.14 moles of copper 2 oxide. So meaning that the copper here, the copper 2 oxide is the what, is the limiting reagent. Okay, again here there's a really quick funny way in which we can figure out these more ratios, but again this is the most straightforward way, the most commonly used way, so this should be more than enough. Okay, because what others do is that they'll be able to write up things such as, and I'm just writing this so that you can have an idea about it, but what we've written so far is enough. So there are some people who say, okay, let's say the moles of copper 2 oxide and then the moles of ammonia, what are their ratios? The ratios we figured out it was 3 to 2. So then they'll say, okay, so it's 1.5. So that's according to the equation. Then the actual moles. So then they want to compare the actual moles. So the actual moles as because what I've written, that's according to the equation. Okay, what I wrote first is according to the equation, right? To the balanced equation. So now they will then get uh the actual moles, in this case 1.14 and then 1.06, and say okay, here we're getting 1.08. So what does this mean? It means that this is less than the amount on top, so it means that the copper is what, is less than it should be according to the ratio. So again, all these things, but like I said, the first method that we did, that's the best one. I'm just showing you these things so that you should have a good wide scope. So since we now know that copper 2 oxide is the limiting reagent, so what we are going to do is we are going to use the moles of copper and the mole ratio between the copper and the what, and the nitrogen, which is the product of interest. Since uh, we are finding the amount of nitrogen produced. So first things first, you want to state, to say copper 2 oxide, what is the limiting, since the question was asking, so is the limiting reactant. Okay, and then what do we know? The moles of the copper 2 oxide is what, 1.14. So these are the moles that we are going to use. So let's now figure out the mole ratio of the balanced equation between the copper 2 oxide and the nitrogen. So we figure out that it's actually 3 moles. So it's 3 moles of copper oxide is equals to 1 mole of what? Of nitrogen. And then from here again, so we know the moles that we're going to use. Again, remember what I said, the moles for the compound that you have, or that you want rather, are the ones that are going to be what on top, the numerator. So here we want to find the number of moles for the nitrogen. So that's why the nitrogen is the numerator. So there you have it like that. So that those can cancel. So you are dividing those moles by what? By 3, which gives you 0.38 moles of what? Of nitrogen. So meaning we have the moles of nitrogen, but the question is asking us to what? Is asking us to find the how many grams. Okay, so they're asking for the mass. So we're asking for the mass. So what we are going to do is we are going to then say, how do we find the mass? So we say mass is what? Moles times molar mass. So molar mass, again, we know this is going to be what? It's going to be 28.02. That's the molar mass of hydrogen molecule. Remember, it's N2. So you multiply these, the moles cancel, you're remaining with grams. So that's going to be what? 10.6 grams of nitrogen. So basically, that's how you want to handle this. Now, there's another concept which we call now the percentage yield. So basically, what the percentage yield is all about is, for instance, in this equation, right? So the amount that we calculated for the ammonia being 10.2, that's the, oh sorry, 10.6, isn't it? So the amount that we calculated for the ammonia being 10.6 grams, that's the theoretical yield. That's the theoretical amount. That's the amount that in theory we would expect uh, this reaction to produce. That's the maximum amount that can be produced. But however, this rarely happens, right? It's rare for a particular equation to produce the what? It's rare for a particular equation to produce the actual amount, okay? And this can be as a result of the side reactions, other reactions that involve one or more of the reactants or products. So you can find that maybe when the reaction is occurring, the reactants are being used in other side reactions which you don't know of. And then there are also other things such as when you're collecting your nitrogen, your product, perhaps you might leave some in the container, you might leave some in the beaker. So there are all those things which are going to be there, so much that the actual yield, the actual amount of the product that you get, okay, after you've done the reaction, now the actual amount that you're going to get, that's actually what we call the actual yield. So then you want now to find the percentage yield. So the percentage yield is the actual yield, which is the amount which you've collected from the reaction over the amount which you were expected to collect if there were no side reactions, any product lost in the process of collection, etc., etc., right? So that's the equation. The actual yield over theoretical yield times 100% is gives you percentage yield. And percent yield is very important as it's an indicator of the efficiency of a particular laboratory or industrial reaction. Imagine you want to produce nitrogen and your percentage yield is, let's say, 20%. That's really poor, okay, because it means that 80% of your reactants are going to waste, for lack of a better term. So percentage yield is very, very important. So now let's answer now the percentage yield for this equation. So we know that the theoretical yield is the 10.6 grams that we found. Then we are told that actually the amount which they actually got from this reaction was what? Was 6.63 grams. So then we know that our actual yield is 6.63 grams, and the theoretical yield is what? Is 10.6 grams. So we can figure out what the percentage yield is. So it's going to be percent yield. So percent yield is going to be actual yield over theoretical yield. over the theoretical yield, again times 100,000. Oh, sorry, times 100%. So again here we know that the actuals we've been told it's 6.63 grams over the theoretical yield. It's saying it's what, 10.6 grams times 100%. So what's the percentage? So the percentage yield is what gives us 62.5%. So that's the percentage yield of this particular equation. So that's a little bit fair, I would say. Yeah. So the next time we meet, we'll do the last example, then we start the next topic. Okay. Any questions?